Okay, we are back. We are on section 5.7, which is all about the natural log function, and this entire section is just anti-differentiation and integration. So there's actually nothing new here at all, the way we learned it. So hopefully this is just a bunch of problems for you to do. Let's see how fast and how well I can do them. And okay, let's just go. So here 5 is just an anti-differentiation problem, 1 over 3 minus 2x dx. And I think that the thing to do here is just do a use of. So okay, so we let u be 3 minus 2x. Du dx is negative 2, and therefore du is negative 2x, sorry, negative 2 dx. And then we do that thing that we have been doing where we need there to be a negative 2, but it's not there. So we stick it in, we undo the damage with a negative 1/2, and this whole thing becomes negative 1/2 du over u. Why was that a good idea? Because now that's ln u, so this whole thing becomes negative ln absolute value u plus c, or the real answer is negative 1/2 ln absolute value 3 minus 2x. Okay, of course, most people won't leave it like this. They will get fancy, and they will pop that negative 1/2 up. And so you might see this written as ln of 1 over root 3 minus 2x. Something like that, plus c. That is how people will write it, because that is 3 minus 2x to the negative 1/2 is 1 over root 3 minus 2x. Okay, 1 down, many to go. Woo, looking good. Okay, 13. So that was just like kind of the easy warm-up. 13 is a nice little problem. What's the antiderivative of x squared minus 3x plus 2 over x plus 1? X squared minus 3x plus 2 over x plus 1. Okay, let's go. This is going to be a rational function. Well, it just is a rational function in which the degree of the numerator is greater than the degree of the denominator. So I basically have to do polynomial long division. This is just testing, do you sort of know to do that? And I do know to do that. So I do polynomial long division right now. How many times does x plus 1 go in? Well, x times, and that gives me x squared plus x. I subtract, and I get negative 4x plus 2. That goes in minus 4 times, and that gives me negative 4x plus 4. And sure, then I get, when I subtract, I get negative 2. Make sure I'm just double checking that for some reason. Yeah, sure. That's, oh no, minus 4. Negative 4x minus 4, I meant to say. So 2 minus negative 4 will give me 6. Okay, so if I did that correctly, man, I hope I did. What did I just learn? I just learned that this expression x squared minus 3x plus 2 over x plus 1 is really x minus 4 plus 6 over x plus 1. And now this is very easy to anti-differentiate. You just do it term by term. So we get x squared over 2 minus 4x plus 6 ln absolute value x plus 1 plus c. Cool. Good. 27. What's 27? Ooh, this is one of these kind of crazy ones. Okay, so what's the antiderivative of root x over root x minus 3? And here they say, hey, hint, let the denominator be u. And okay, that's actually a kind of idea that maybe shouldn't be so crazy to you, because after all, we want our denominator, if possible, to be a single term. We practiced some problems like this the other week. So what am I going to do? Taking a hint from the book, I'm going to let u be root x minus 3. Is this a good idea? I don't know. Let's find out. What's du dx? Well, du dx is the derivative of negative 3 is 0. The derivative of root x is 1 over 2 root x. And so what we get is, let's see, well, what we get is solving for dx. dx I get is 2 root x du. But now the real goal here is to rewrite this problem as an antidifferentiation problem with respect to u. So I see already immediately that the numerator is there's like a root x in there. So maybe one thing I should do, well, is solve for root x. And another thing I need to do is solve for, well, okay, so I'll maybe do that now. What is root x? Root x is just u plus 3. And why that's relevant is that here I want to substitute for the dx. I want to replace dx. I want to rewrite dx in terms of u. So here dx, I solved for dx. Well, I got u. I differentiated it. I solved for dx. But now there's like a root x expression in here. So okay. So what I really mean by that is that I now rewrite this as dx equals 2. What is root x? Well, it's u plus 3 du. And now this is kind of everything I need. I take this and I substitute in for dx. I take this and I substitute it in for root x. And I take this and I substitute it in for the denominator. I hope I did that whole thing right. I think I did. And so what do I get? This whole thing turns into so root x u plus 3 dx is another sort of 2 u plus 3 du. So 2 u plus 3 du, and the bottom becomes just u. All right. So this problem becomes now u plus 3 squared over u du. And that's just really great because this is now just a rational function. And in fact, this is going to be quite easy, I think, because this numerator can be rewritten as u squared plus 6u plus 9 over u, and then I just divide. And so my actual problem turns out to be very easy. It's u plus 6 plus 9 over u du. And I know exactly how to anti-differentiate that. And why, so looking back now, we see why we could have come up with this idea, even if the book hadn't given us the tip to make that denominator u, because there's just this huge power in having my denominator be a single term like this. When it's a single term, it means that I can then split up my rational function like this, and everything's just great. Okay. Whew, what do we end up with? This is 2 times the antiderivative of u is u squared over 2. That's 6u, and that's 9 ln absolute value u. And so, plus c. And so what I get as my kind of final answer is u squared, so root x minus 3 quantity squared from distributing, plus 12u, but u is root x minus 3, plus 9 ln absolute value root x minus 3 plus c. Root x minus 3 plus c. Okay, and it's tempting to leave it like this, and if you left it like this, it wouldn't be wrong, but many people will distribute and then throw out constants. So if you kind of want to just keep going, this becomes x when then you get minus 6 root x plus 9 plus 12 root x minus 36 and then plus the logarithm. And so then I can not only combine like terms to get x plus 6 root x, but I can just throw away this 9 and this 36 because they're just constants and I don't care about constants. So actually my final answer is x plus 6 root x plus 9 ln absolute value root x minus 3 plus c. And that's what that's what a computer will tell you the answer is, I suppose. Okay, well I'm just gonna get to the answer key I should probably check these, because if I'm making a mistake, it would make more sense to catch it now. Oh, I have made a mistake? 9, oh, I made a tiny mistake, which is, when I was distributing the 2, I forgot to distribute to the 9, so really that should be 18, and that's 18. But otherwise, I think everything else was right. It was. That is so good. Okay. Good. And these other ones are right too. Minus first plus 6 ln. Yeah. Okay. Good. One more of these, I think, that are just anti-differentiation. So this was, I don't want to call it sort of warm-up, but this was, we spent 2 whole weeks doing like a bajillion anti-differentiation problems. And then maybe there was like a week where we didn't do any anti-differentiation because we were learning the fundamental theorem of calculus. So now, let's get this skill back again. 37 says, can you do the antiderivative of e to the negative x tan e to the negative x? Okay, and well, there are some clear things to do here, I think. First of all, we can, it certainly looks like some chain rule happened here. This inner function should be subbed out. So if I let u be e to the negative x, then du dx is the derivative of that, which the derivative of e to the negative x is e to the negative x back inside negative 1. And so I get du is just negative e to the negative x dx. And therefore, I stick a negative in there and also on the outside, and it means that I can rewrite this as negative antiderivative tan u. Okay, and it might be that you just know the derivative of tan u by heart by now, but if you don't, it's in this section that our book learns this fact for the first time that we learned 3 weeks ago. The way you do this, if you just forgot or whatever, who knows what, is you rewrite it as sine u du over cosine u, and then you just do another kind of substitution. So now you say, let w be the bottom, let w be cosine u, and then dw is going to be the derivative of cosine is negative sine u du. And in this case, the negative is already just there. Maybe we don't even need to take it out, we just leave it there. And so I can do a direct replacement of this is sort of dw over w. And all the problems in this section 5.7, have to do with using the derivative of natural log is 1 over x. And so all of these problems are anti-differentiation problems and integration problems, which exploit that rule to sort of go backwards. So it's only now that our textbook is learning how to do this. What do we get? We get ln absolute value w, which is why this is really ln absolute value cosine u, and it's really ln absolute value cosine of e to the negative x. Boom, 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 plus e. Okay, so that was 4 anti-differentiation problems. All of that was just kind of review, to be honest. So there was really just nothing new happened in all 4 of those problems that we just did. Those are problems that we had already been kind of doing for a couple weeks now. So I'll just erase this. And so let's see. Yeah. So that took me 15 minutes. Maybe it would take you longer. I don't know. Okay, 49. Finally, we're moving on to like the real stuff now. Real stuff. let's do some integrals. So this is the integral from 0 to 4 of 5 over 3x plus 1 dx. And I'm really going to push doing this like the good way. So what's the good way? The good way is integration by substitution. So in fact, everything we're about to do is going to look very similar to what we have just been doing for the last 10 minutes. Now I'm going to let u be 3x plus 1, du dx is just going to be 3, so du is just 3 dx, and it's still true that I stick in a 3 and I undo the damage with a 1/3. Which is why I get 5/3 on the outside, and 3 dx becomes a du, and u on the bottom. Alright, because I'm doing integration, with substitution, I have to be aware that this 0 and this 4 are x values. They're where to start on the x-axis and where to end on the x-axis, but I am interested in transforming this integral into an integral involving just u's. So I need to transform these x's into u's. Well, when x is 0, u is 1, and when x is 4, u is 13. So this is now the integral from 1 to 13 of d over u. And I don't look back. All I have to do now is just do this integral. This integral is like a number, and it's equal to that number. Okay, so what is this? It's 5/3 ln absolute value of u, but evaluated at 13 and 1. And so what I get is 5/3 times, ln 13 minus ln 1, but ln 1 is just 0, and so this whole thing becomes 5/3 times ln 13. And so that's just some gross number, and whatever that is, it is the answer. Woo! Good. 5 to go. 53 is another problem. It says, hey, take the integral from 0 to 2 of x squared minus 2 over x plus 1. Okay, well now, just like what happened earlier, I need to do some polynomial division. So what is x squared plus 0x minus 2 is the way to do it. Divided by x plus 1, well it's going to go in x times. I got x squared plus x minus 2, that goes in minus 1 times, minus x minus 1, 2, negative 2, minus 6 minus negative 1. Just quickly double check that. Boom, 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 boom. Negative x. Negative 2 minus 6 minus 1. Yeah. So this whole problem was really the problem of what's the integral from 0 to 2 of x minus 1 over x plus 1. Okay, and now I can just finish this off because I know how to anti-differentiate this. It's just going to be x squared over 2 minus x minus ln absolute value x plus 1. And you can just double check that if you differentiate this, you just get that. Okay, but all evaluated at 2 and 0. So when x is 2, I get 2 minus 2 minus ln 3 minus when x is 0, I get 0 minus 0, but and then ln of 1 is also 0. So I guess this whole thing just becomes negative ln 3 is just the whole answer to this problem if I did it correctly, and I did. Woo! 70. Moving right along here, 70 says, find the area of the given region, and this just boils down to the integral from 2 to 4 of the 2 over x ln x function. So they give you a graph of the 2 over x ln x function, and they ask you to find it's positive, and they ask you to find the shaded region. The shaded region is just from 2 to 4, so this is really just this integral. Okay, how do we do this integral? I know how because I see that some chain rule happens here. In particular, the derivative of natural log is 1 over x. And therefore, if I let u be ln x, then du is 1 over x dx. And 1 over x dx is just exactly what's sitting there. And so this problem is more or less done. This becomes 2, that 2 wasn't really doing anything. This becomes 1 over u. Am I doing this right? 1 over u du. Yeah, because u is, ln x is u, and 1 over x dx is du. So yeah, this is just 1 over u du. I have to change the bounds. So this is now ln2 and ln4. Because when x is 2, u is ln2. But now I have to do this integral, but this integral is going to be, well, it's natural log again, right? So this becomes 2 natural log of u, but evaluated at ln4 and ln2. Yeah, so what's the smooth way to do this? Well, okay, so I get 2 times, well, it's just ln4 minus ln2 then, right? So ln4 minus ln2. And what is ln4 minus ln2 by a log rule? That's ln, well, that's 2 times ln of 4 over 2, otherwise known as 2. So it's 2 ln2. But most people would pop that 2 back up now and would give the final answer as ln4. So, okay, a lot of fancy business there. Just gonna double check that, but yeah, that's just right. Okay, good. 71. I'm just very good at log properties because I'm a pre-calc teacher. So that was just no problem for me. But for you, maybe watch on 1 times speed or something. 71. Okay, this was just unnecessary, I think, to do this problem. They give you a graph of tan. They want the area between 0 and pi over 4. So this is just literally, dude, what's the integral from 0 to pi over 4 of tan? At this point, maybe it's nice to just know the antiderivative of tan. I do. It's ln secant. So I'm just going to tell you that this is ln secant x evaluated at pi over 4 and 0. Do you want me to go through that whole thing again? I probably don't want to. I could. It's almost identical to the derivation from 10 minutes ago. The only difference is, you have sine over cosine, and so you do a substitution. In this case, you let u be cosine, but then there's like this extra negative in there because the derivative of cosine is negative sine, not sine. And then what you get is negative ln u, but then that's really negative ln cosine, and people use the negative rule to pop that up, so this is really ln of 1 over cosine. So that's how you get ln of secant. Okay, you can just do that every time, or you can just learn that because it just comes up a lot. So anyway, here we are. How do we finish this off? This is going to be the ln of, what is the secant of pi over 4? Yeah, it's just root 2. So this is going to be ln of root 2 minus ln of, now we have to be a little bit careful here, well, not really, but secant of 0 is 1, ln of 1 is 0, so the answer to this problem is just ln root 2. Okay, and I got nothing to say about that. Woo! Good. 2 problems left to go. It's like very late at night. Maybe I should try to be more pumped and exciting. 2 problems left. Woo! My goal is to make this video less than 33 minutes. I think I'm going to succeed, unless these last 2 problems are really hard. All right, let's get serious here. Woo! 75 and 91 I shall do. 75. 75 says, hey, find the area of the region bounded by the graphs of the equations. Okay, and here we are given the curve y equals 2 secant pi x over 6, and x equals 0, x equals 2, and y equals 0. Okay, so you probably need a picture of this. Well, okay, this is a kind of a thing that we learn how to do in pre-calc to know what secant looks like on this interval, and then the pi over 6 is going to, pi over 6 is about half, so it's going to stretch everything out by a factor of basically like 2 or something. But anyway, we're only going to x equals 2. So where are we? Where are we when x is 0? When x is 0, secant of 0 is 1. So we're going to be up here at 2. And then this is going to be a bad graph I see now, because secant is going to get bigger over this interval. So here's 2, boom, at 0. But when I plug in 2, I shall get pi over 3. Secant pi over 3 is 2. And so that's just true. And so this is going to be up here at 4. Alright, so here I have just graphed by hand what I know the secant function to look like, and therefore they want me to find the area enclosed by this secant curve, and x equals 0, x equals 2, and y equals 0. So they really just want me to find the area of this curve, man. And okay, I can do that with integration, and so the answer to this problem is just going to be the integral from 0 to 2 of 2 secant pi x over 6. Okay, so that's really all that's going on. And okay, let's do a substitution. So let's let u be pi over 6 x. And then, of course, du will just be pi over 6 times dx. And so I need there to be a pi over 6 in there, so I put a 6 over pi on the outside. And thus, what I really get here is 12 over pi times, this is now just secant u and du. And I'm going to change my limits as I go. So, okay, when x is 0, u is 0. When x is 2, u is pi over 3. Okay, so now it all just boils down to, dude, do you know how to anti-differentiate secant? And this is something we did 2 weeks ago. Our book is just learning how to do it now, because the way you do it is with this crazy idea that you would never think of in a million years of multiplying the top and bottom by secant u plus tan u. Okay, why is this such a good idea? Because now when you go to multiply this out, you get 12 over pi times the integral from 0 to pi over 3 of, and the top becomes secant squared u plus secant u tan u all over secant u plus tan u du. And if I do one more substitution, I'm determined to squeeze this in on this left board here. So I'm going to let the w or something be that whole bottom. So if w is secant u plus tan u, then the derivative of secant is secant tan, and the derivative of tan is secant squared. And so that entire numerator becomes exactly the derivative of the top. And that means that this whole thing becomes 12 over pi times just dw over w. And I will once again change my limits, I guess, as I go. Because now w is secant u plus tan u, and that's the derivative dw up there. Okay, when, let's see, when u is 0, what is w? Well, it's going to be secant 0 plus tan 0. Well, secant 0 is 1, tan 0 is 1. And what's secant pi over 3 plus tan pi over 3? Secant pi over 3 is a half, and tan pi over 3 is root 3. So this is 2 rather. So 2 plus root 3. Okay, so after all this work, I get that this whole thing is going to be 12 over pi times, of course the antiderivative of this is ln w. So we get ln w evaluated at 2 plus pi over 3 and 1. Hope you guys are following all this. I'm going kind of fast, I guess. I just like to know all this stuff. So I get 12 over pi times, and that's it. I get ln of that minus ln of 1, which is 0. So I'm just going to get that times the natural log of 2 plus root 3. That's my final answer right there. And I bet it's right. 12 is done. Yeah. Okay, so what did you have to know to do this problem? You basically just needed to know the antiderivative of secant, I suppose. Or remember that this is the general method to do it. And if you actually had memorized the antiderivative of secant somehow, you could just maybe have gone even faster. Okay, last problem is number 91. Number 91 says, find the average value of ln x. Okay, find the average value of f of x equals ln x over x on the interval 1e. Okay, this is a little bit repetitive because we kind of did a problem like this like 10 minutes ago. But anyway, what is the average value? Well, it's going to be 1 over the width of the interval, so 1 over e minus 1, times the integral from 1 to e of ln x over x dx. So without reviewing that, that's what average value is. The average value of a function on an integral is just the integral over that interval divided by the width of that interval. So now I just have to figure out what this integral is, but I think I know what to do because we just did a problem like this, or very similar. If I let u be ln x, then du is just 1 over x dx, and that's exactly what I just have sitting there. So this becomes 1 over e minus 1 times the integral of just u du. And now I have to change my limits of integration. When x is 1, ln of 1 is 0, so this becomes from 0 to, and when x is e, ln of e is 1. Yeah. So, okay, I don't even need calculus for this. This is just going to be a half because it's just a line, but I guess we could just do it. So 1 over e minus 1 times the antiderivative of this, so it's going to be